All right. So welcome everyone to this live Q&A session of the final promotion conference on Offshore HVDC Grid Technology. So what's the final conference of promotion? Promotion is a research project on progress on meshed HVDC offshore transmission networks. And of course, we would have liked to do a physical final conference event, but with the current circumstances, this is not possible. So we designed an online conference with a lot of breakout sessions for you, where we have our 4.5 years of research presented in over 80 pre-recorded presentations, which you might have had a look at already, and to give you the chance to discuss these pre-recordings, also our key results, we now have this live Q&A breakout session today. My name is Christina Brandl. I'm a research associate with RWTH Aachen University, and within the project, I had the lead on work package 2 on convergence and topologies. I was also involved in other work packages on the wind turbines, the protection, and especially on in work package 11 on the harmonization towards standardization. Within this breakout session, we'd like to provide you an overview of the contributions to offshore HVDC grid technology that took place within the promotion project. And then we'll also give you shortly the key messages from the technical work packages and offer a Q&A session for each of these work packages, so you can directly get in contact with us, not only have the pre-recordings. And in the end, we'll prepare conclusions and outlook that we see from our perspective right now. So if we look at what we've done in the past few years, the existing state-of-the-art for offshore wind integration are point-to-point connections. But with more and more wind integrated and different interconnectors realized with HVDC technology, there's the idea to connect all these to multi-terminal grids, having more reliability, interconnecting the different options. And for these new type of grids, we need new components. So for example, HVDC systems to reduce the footprint of the offshore platforms. These systems need dedicated DC side protection systems, so we can limit the impact of the faults on the overall system. So there has been a lot of research on DC protection system, for example, concerning the algorithms and the corresponding concepts that can be applied. And then, of course, the new component for this grid are the DC circuit breakers, with different types proposed in the recent years. And promotion has fostered the understanding of these different topologies and how they can be integrated and tested. Then, of course, with more offshore wind farms being integrated, the controls of the wind farms become more and more important. And within the project, we have analyzed how we can actually use those controls to, for example, facilitate diode rectifier integration, or also use those capabilities for black start. And then, of course, the overall system is based on the control concepts. So we have to make sure that there are suitable control concepts for a broad range of scenarios for the different components and that they all work together. So this is the overall field of challenges and also aspects that we covered within the technical work packages within promotion for offshore meshed HVDC grids. So to give you a brief overview of who's going to present what in this breakout session, we're going to start with the HVDC GIS technology demonstrator presented by Uwe Richard from ABB Hitachi Power Grids. And then we'll move on to the HVDC circuit breaker performance characterization, which was led by Dragan Jovcic from the University of Aberdeen. We'll have a presentation on the HVDC Grid Protection system presented by Dirk van Hertem from KU Leuven. We also cover the topic on wind turbine generator converter interaction presented by Nikolaos Koutouloulis from DTU. I will present on grid topology and converters. And then in the end, we'll conclude with the key aspects from harmonization towards standardization presented by Paul Sorensen, also from DTU. For this general breakout session, a general note, please note that this event will be recorded and published on the promotion website, so you can also come back to it. And then we'll have the key messages from each work package presented here in this 2-hour session. And afterwards, there's time for a 10-minute Q&A session. If you have any questions, please use the chat provided with the GoToMeeting, stating your name and the relevant presentation and presenter. So if you have any questions to the pre-recordings that were released on Monday, you can also raise them here and we'll answer them. We have several of the presenters also online, either the corresponding presenters here in this session or the presenters of the videos can answer you directly. We'll try to answer as many questions as possible after each presentation. If there are any questions left over, or if you have any other questions after the session, please always feel free to contact us, either the speaker or presenter, if you have any further questions. So with this, I'd like to hand over to Uwe and present the work package 15 on HVDC GIS technologies.
Yeah, hello, good morning also from my side. My name is Uwe Richert. I'm with ABB Hitachi Power Grid since more than 20 years now. And within promotion, I was and I am responsible for work package 15 as a project leader. And it's really a pleasure for me to give you some key messages now from work package 15. Next slide, please. Yes, what you could see here is a GIS prototype installation test. The, let's say, biggest part of our project was to perform such a long-term prototype installation test in the laboratories of KEMA in the Netherlands. There is one picture on the right side where you could see the test, including the test equipment from the lab. And on the left side, there is a picture of our last demonstration event that was in the beginning of this year, together with the performance demonstration of an HVDC breaker from Hitachi ABB. The prototype installation test is now finished, and that means that we have verified the overall performance of the manufacturer to produce and install an HVDC GIS. And we can say now that it can be expected that an HVDC GIS components will have an equally long lifetime as known from HVAC GIS. Some words about the background for that. So if you use an HVDC GIS switchyard on a platform, which is required for HVDC offshore grids, then you can reduce the space for the HVDC switchyard by 70 to 95%. That means in total roughly 10% for the platform, for the HVDC platform. I want to say also that the cooperation in work package 15 was characterized by a very high degree of openness, by scientific interest, great experience, and close collaboration. And the group was very well composed. So you could see on the right side also the members of the work package 15. So including TSOs, test laboratories, a research institute, consultancy, a university, and a manufacturer. Next slide, please. Yeah, let me now go to the key technical conclusions. Again, the most important thing is that we have increased the technology readiness level for gas insulated HVDC substation. So the technology readiness level is increased from 6 to 8. The recommendations for specifying a gas insulated HVDC system were developed, and moreover, the testing requirements, procedures, and methods were developed based on own simulation analysis, real HVDC onshore and offshore experiences, and also based and worked together hand in hand with Seagray. You could find 2 videos prepared for this breakout session, one about the test setup itself and the second one about the test equipment, so the HVDC GIS. The long-term test was carried out according to the developed test requirements and procedures, and the results were used to improve the models and to develop the understanding of possible failure modes. Work package 15 was also very active in preparing standardization work in Seagray and ISC, and we will learn more about that topic later on in this session. Next slide, please. Besides the mentioned prototype installation test, we had 2 more interesting tasks within the work package 15. The first one deals with monitoring and diagnostic methods of partial discharges. Main responsible contact person here is the Technical University of Delft. An alternative monitoring and diagnostic method was researched based on magnetic detection, in contrast to the well-known conventional capacitive detection in HV ACGIS. Moreover, concepts such as the PD localization and charge estimation were investigated and proved feasible for a critical offshore installation. There is one video from the University of Delft specifically about that topic. Another really important part of our work package was the investigation of the performance of the existing monitoring and diagnostics methods for new gases as alternative solution for SF6. So that means future direction of an SF6-free HVDC GIS. And the second, you could see also the test setup. So typically we have used typical defects from a GIS, that means particles on conductors and particles on insulators, and verified the performance and compared the experiment results with the well-known behavior of SF6. And there was also one presentation prepared about that topic from the Supergrid Institute in France. Yeah, next slide. Before I finish, I want to mention also that we have prepared a lot of reports in Work Package 15. In total 8, 4 are already published on the web page. One document on recommendations for specifying an HVDC GIS system, a second one describing the test requirements, procedures and methods. One report about the diagnostic and monitoring tools and methods, and another one about the characteristic of different gases under PD compared with SF6. The other 4 are under revision now, and it's planned to publish it latest at the end of September. Next slide. I think that was my last slide, and now we are happy to answer questions.
So there are no questions in the chat yet. We received some questions beforehand. I'll just open those. Can you see the questions?
Yes.
Perfect.
Yes.
We can...
Yes. Thanks for the question. Maybe you can unmute directly the person who could give the best answer. So for the first question, I would propose to unmute Michael Gatscher. He is in the call. I see it. Who can unmute the person?
It's in the
already.
process.
Okay, Michael.
Hello, everyone. Can you hear me?
Yes.
Okay. The first question: is it necessary to repeat the test if the current rating increases to 5,000 amps? What if rated voltage increases to 550 kV? Yes, maybe. Generally, this test, the prototype installation test that we performed within promotion, is not a mandatory test in the sense of a type test. So generally, if you are a user looking for an HVDC GIS, it is not mandatory to have this test performed. However, of course, it is kind of a replacement for operational experience because of the new technology. If we now increase the current rating from 4,000 to 5,000 amps, I think this is something that maybe needs upgraded conductors or something like that, where a repetition of the whole test is not necessary. I would just look maybe at type tests that the temperature difference between conductor and enclosure does not increase by a factor of 2, something like that, with this current increase. And then I think the technology is still qualified. On the other hand, when we increase the voltage level from 320 to 500 or 550 kV, there are some relevant changes also in the design of the HVDC GIS. So where we right now do not yet have operational experience, so the recommendation would be to do a test like this for 500 kV HVDC GIS. But in general, it's not necessary, and if there is, or not mandatory, if there is operational experience or high trust in the technology, then yeah, you can also rely on the type tests.
Yeah, yes, thanks, Michael. Can you also go to the last question directly?
Yes, why was an SF6 to air bushing instead of a cable termination used? Yes, from the manufacturer point of view or from the work package point of view, if we would have used a cable termination, which is of course very relevant for offshore applications, we would have actually been limited with the impulse over voltages. And from the GIS perspective, an overhead line application with higher over voltages is more stressful, so we decided for the bushings to test dielectrically more critical case for the GIS. A cable termination would be available. We have done a qualification and type tests and pre-qualification tests with one manufacturer. And if GIS cable termination sealing ends need to be type tested, which standard should be followed? Yeah, so what we did, based on a cable test procedure or GIS test procedure, that's the full question. So basically, in this case, it was done for with the cable procedure, and for the GIS itself, we did the GIS type tests. So in this case, we more or less followed both the standards. If it follows cable standard or requirements, is there an additional requirement for GIS enclosure need to be considered or not? Yeah, so when we do both tests, of course, everything is covered. What would be very good for the future is that there is a common understanding of how to qualify a cable sealing end for a GIS independent of manufacturer, so that several manufacturers can interoperate, so that not for every combination of GIS manufacturer and cable sealing end, this whole qualification procedure has to be repeated. And for this, also out of promotion, and secret working group was started to define common test procedures. So if you're interested in that topic, I can also recommend joining this working group.
Yeah. And I want to mention also that we have started a secret working group on this topic. Thank you, Michael. Is Luis also in the line? Then maybe he can answer to the second question about the magnetic detection antenna.
Good morning, everybody. Yes, can you hear me?
Yes.
Okay. Yeah, sure. Thank you very much for the question. Basically, I would like to mention that well, currently the UHF method is kind of like the standard monitoring technique for PD on GIS and let's say AC GIS. And basically they have gained like very high popularity just because they are very sensitive, and also because they are very resilient to noise. However, let's say there is some kind of drawbacks with this method, and is that first they might suffer from a spatial sensitivity, because actually the electromagnetic waves, they are heavily attenuated as they are traveling along the GIS. So that therefore it's necessary to deploy like a number of UHF couplers, I mean, along the GIS. So this can obviously increase the hardware requirements and the complexity of the system. And also it's a little bit it might be a little bit challenging to compare like the results, because you know you are basically using the peak amplitude of the voltage signal. So it's a little bit tricky to compute like PD related parameters. So therefore, here in the University of Delft, we have in this working package, we have been researching an alternative and like a complementary technique for PD detection based on a magnetic antenna. in our case, what we are researching is basically to use to shift the detection towards the lower frequencies, actually, where the signal or the, let's say, the PD pulse is less attenuated than in the compared to the UHF couplers or like range, let's say. And we have developed basically it's a magnetic loop antenna, and then this antenna is installed in the GIS compartments, and because it works in a much lower frequency range, so we have proof that the spatial sensitivity is let's say it's quite good. We have done like laboratory experiments where we have measured, like we have located a PD test cell in one end of the GIS, and we have measured, like after 25 meters away from the test cell, we have measured with our antennas, and still with very good signal to noise ratio. And the second, let's say, advantage of these methods is that we were able to calculate or to estimate the charge of the PD signal, which is kind of like a milestone in the state of the art, because as you know, like theoretically, it's not possible to measure the charge of the PD using the UHF methods, just basically because the couplers are tuned in such a high frequency that you basically are missing all of the low components, and therefore it's not really feasible to measure the charge. But in our case, it's the sensors are tuned in such a low frequency that we have been able to estimate the charge of calibrated pulses and also the PD signals from a test cell, with a very like reasonable and very good error. So I think that those are the main two advantages, and those are the reasons of why the method that we research in this working package like stands out, or let's say away from the UHF traditional method.
Yeah, thank you, Luis.
Yes, okay, thank you very much.
It's important really to be able to describe the risk of defects detected in a GIS system. And finally, we have two questions for the new gases, and I see Katerina on the panel list. Could you give an answer to the last two questions, or to the third and fourth question?
Yes. Hello, can you hear me?
Yes.
Yeah, okay, perfect. Good morning to everyone. And yeah, so in fact, within this project in SuperGrid, we studied different alternative gases, including the fluoronitril in CO2 mixture and fluoroketone with air mixture. And as we studied different type of defect, and also in short and long-term application. And in all these cases, we've seen that there was an higher repetition frequency for all the alternative gases that we studied with respect to SF6. And in fact, we think that the main reason is the fact that compared to SF6, the alternative gases are a mixture of gases with an high attachment power in a buffer gases, CO2 or air. And the fact that the repetition frequency is higher for the alternative gases can be mainly due to the presence of the buffer gases. So all the phenomena are driven more than for the presence of the buffer gases in respect to SF6.
Yeah, thank you, Katerina. So finally, thanks to our contributors. And
there's one question from the chat. Maybe we can still answer this in the question section. I'll just read it out. Will SF6 be banned in EU in near future due to greenhouse impact?
Yeah, in fact, the fact is that SF6 has a very high global warming potential and is already in the list of the gases that has to be banned. So the idea is right now to find the alternative that can be used in our cases in high voltage equipment. But the SF6 is not only used in the distribution equipment, is also the main contribution of SF6 is also in other type of industry. But the point is in switch gear, it's now evident that we can have also alternatives, so we can use this alternative instead of SF6. So yes, when right now there's already equipment that use other gases instead of SF6. So it's become it's a real fact that we can use other gases than SF6.
All right.
Okay. Yes,
And
thanks. Let me say some final words, work package 15. So of course we are happy to answer all further questions. So if you have further questions, you can send it to us directly. And the second thing is that we are preparing a workshop dealing with HVDC GIS as the final workshop of the work package 15. And most probably that will be held in end of September. So then you will get more information about that. Thanks from work package 15.
Right, thank you very much. So we'll move on to work package, that's wrong, work package 6 on HVDC circuit breaker performance characterization. Dragan, the stage is yours. We can't hear you yet.
Okay, good morning, colleagues. Hope you can hear me now.
Yes.
Good. Can we move to the next slide, please?
Sure.
So welcome to Work Package 6 presentation. My name is Dragan Jovcic. I'm a professor at University of Aberdeen. I'm a director of Aberdeen HVDC Research Center. In the promotion project, I have been Work Package 6 leader. Can we move to next slide, please? The main purpose of Work Package 6 has been to increase understanding of DC circuit breakers and to provide the support for various other work packages which perform the demonstration and testing in the promotion project. We studied 4 different DC circuit breaker technologies. For a hybrid DC circuit breaker, various models have been developed at various levels of accuracy and complexity, and the operation has been analyzed and demonstrated on a common test DC grid. So we have agreed on the test grid with our grid operator partners and considered each of the technology on the same test grid. For current injection DC circuit breaker, similarly, a model has been developed for various levels of accuracy and complexity. Here, we put a lot of effort also on developing a roadmap for scaling to higher voltages, because this technology at the beginning of the promotion project was developed at slightly lower level than hybrid, lower ratings. Similarly for VARC, a VSC-assisted DC circuit breaker, various models have been developed. A roadmap for scaling to extra high voltage is available, and the operation has been demonstrated on the common DC test grid. Thyristor-based HVDC circuit breaker has been studied, models have been developed, but this technology was not demonstrated or tested on hardware, and therefore only limited work was done in Work Package 6. Real-time DC circuit breakers are important because they've been used in Work Package 9 for the demonstration of protection and the circuit breaker. So we have developed for each of these 3 technologies real-time models. We have concluded that a small time step modeling would be required for all of these technologies, although a large time step can be used for controller modeling. Next slide, please. A lot of effort was placed on developing a common model and test circuit which could be used for various different DC circuit breaker technologies. So the benefit of this approach is that it enables users to compare various technologies, because so far each manufacturer would have tested their breakers on a different test system and use different modeling approaches. So we've developed a generic model, and we've developed also simplified models which are slightly more complex than generic and different for different technology. We've developed a test circuit which was used for testing each of these DC circuit breaker technologies, and we've developed a test plan with a range of tests which again have been used for each of the technologies. We studied failure mode for a hybrid and mechanical circuit breaker. The main conclusions are that in most cases, this circuit breaker would fail in the closed circuit. So in the case that some of the internal components fail, fault tree diagram method was used, and it was concluded that failure while opening is the most critical. Basically, a single component failure leads to system level consequences. Energy absorber, which consists of a matrix of individual arresters, was studied in some depth, and it was concluded that it is theoretically possible to have a cascaded failure, which is positive feedback, which amplifies the failure following a failure of one component. And we've developed a lab scale demonstrators around 1 kilovolt, 500 ampere, and all of these conclusions have been confirmed on the hardware in the laboratory. There is a lot of ongoing research worldwide and in the promotion project on developing circuit breakers. The key aims are reducing opening time, reducing cost and size, and I'm confident in the future we will see further developments of the technology and possibly some new technologies emerging. In the promotion project, we have made also some advances. I'll just mention a few topics. Disconnector voltage control has been studied, and we have demonstrated that it is possible to reduce the peak current and energy, maybe by around 30%. We've studied also possible reduction of the cost by using a single valve to develop a bidirectional DC circuit breaker, and some new DC circuit breakers topologies have been investigated at very low TRL level. Next slide, please. So this is my. I will not read them. Some are not available in the public domain. For those of you outside the promotion, I would advise you to look at our publications. There is a lot of publications, around 10 journals and 10 conferences if you're interested in any of these topics. And down you can see the list of partners in Work Package 6. So 3 manufacturers, 2 universities, the consultancy company, and the research center. And I will also mention that TENET was informally involved in the last few years. Thank you very much for listening, and I look forward to any questions.
So thank you very much, Dragan. We don't have any slides in the chat yet. We received some previously, so I'll open those. Let's see.
I can't see any question.
Yeah, yes, my PowerPoint is just not opening the slides. I'll try again. There we go. Can you see the slides now?
Yes, I'll read this, Christina. What is the current TRL and ratings for each DC circuit breaker technology? Okay, so this may not be directed to work package 6, but I will briefly mention what we have done in work package 6. So we assumed that application will be related to 2 voltage levels, 320 kilovolt or 525 kilovolt. And in the scaling studies, each of the 3 circuit breaker technologies were targeted for these voltage levels. I shall mention also that DC circuit breaker technologies will always be modular. It turns out that around 70 to 80 kilovolt is the most suitable level for modules for technology studied in this project. So various studies have been performed at the module level, but also at the system level where we connect, let's say, 4 or 6 of these modules in series. Regarding the TRL level, the studies have been performed, well, demonstrations have been performed in work package 10, and you will see more details. I think it's coming next week in the demonstration part of the promotion project. I will briefly mention that hybrid circuit breaker has been tested at 350 kilovolt, 20 kiloampere, active current injection at 160 kilovolt, 16 kiloampere, and VSC assisted resonant breaker at 80 kilovolt, 12 kiloampere. Second question, why is mechanical DCCB requiring real-time modeling small time step? With real-time modeling with RTDS, we have the option to use the small time step around 2 microseconds or the large time step of 50 microseconds. Small time step is used typically with the power electronics. So for hybrid breaker and the VSC assisted breaker, we need to use a small time step, whereas the controller can be developed either in a large or small time step. For the mechanical circuit breaker, I think it's best option if we invite Delft, Marian Popov, to say a few words. I'm not sure if Marian is online.
Yes, I'm online. Thank you for this question. It's very interesting. As Dragan mentioned, not only hybrid and VARC DC circuit breaker, but also mechanical DC circuit breakers must be modeled in small time steps. The reason for this is that the arcing, the current interruption is a high frequency phenomena and deals with a very small time constants, so that in order to take this into account, you must go normally with a time step which is smaller than the arc constant. And this is normally vacuum arc which is used, and the vacuums, they are known that they have a very small arc constant. So therefore, it is important to use small time steps, which in this case, we use 1.4 microseconds. That was the minimum that we can achieve with the existing RTDS technology. Well, now this have another question, how this will have impact on controllers, especially large controllers, in case when you simulate a large network, multi-terminal network, right? But this is, I guess, another question.
Okay, great, thanks, Marian. So the third question is it possible to use generic model and test circuit applicable to all DC circuit breaker topologies? So we have proposed a generic model which consists of ideal switch and arrestor in parallel. The ideal switch has a time delay, and this delay will be dependent on the particular technology. For example, it will be 2 milliseconds for the hybrid breaker, 7 to 8 for the mechanical, and around 3 for arc breaker. So such a model is suitable for system level studies, for power flow, and for example, when we are really studying a large grid, 20, 50 terminals and so on. It is not as accurate as other models, but it provides the placeholder for the circuit breaker, basically for initial feasibility study. It can cover basically all the technologies. Same applies for the test circuit. There are various hardware test circuits for testing DC circuit breakers, because manufacturers use the different test circuits, it's then perhaps somewhat confusing for a prospective user to understand the performance when the results are provided on a different test circuit. So we have proposed a common test circuit, which is a voltage source behind impedance. Impedance can be adjusted. On the DC side, we have a cable model. And then in deliverable 6.9, we have tested each of the different DC circuit breaker technologies on this same model. And on the same test program, we have listed maybe around 10 to 15 typical tests, which really enable all the known performance aspects to be tested, and then it provides the common ground for all different technologies.
Great. Thank you very much. We have 2 more questions in the chat. I'll just read them out. Is the series connected current limiting reactor an integral part of a DC circuit breaker? Is it located external or internal to the DC circuit breaker?
Okay, so this has been debated in the work package 6, and unfortunately we were not able to get a consensus on this. There are different views, and it is evolving, and now I'm involved in the SIGRE B480. Again, this is raising the different views. It is needed for the circuit breaker because it really limits the current to within the rating of the circuit breaker. So this is the argument why it should be part of circuit breaker. But also inductor is necessary for many protection approaches, and one would argue in that case that it is a part of the system of the DC grid, and the TSO should really determine the value of the inductor. I don't know if we will resolve this, and I don't know if it is crucial to be resolved, as long as we have a good understanding what is the purpose of these inductors. We can put it either as a part of circuit breaker or as a part of a DC grid.
All right. Thank you very much, Al. So the second question is, can a DC circuit breaker be also utilized for breaking load currents under normal system operation, for example, for maintenance purposes, or is a DC circuit breaker only meant for clearing faults?
Yes, this is actually an important question, and I mentioned previously that we have proposed a set of typical tests for the circuit breaker, and then purposely one of the tests has been introduced as a load current, and also quite a low load current. I think we specified 0.1 per unit, and in both directions, in fact, either positive or negative direction. So yes, all the circuit breakers can be used for breaking a load current, for connecting, for charging the line, and so on. And I will mention also that some of the technologies have quite a different response when we are breaking low current. And in fact, in some of the DC circuit breaker technologies, it's actually more difficult to interrupt a small current. More difficult means it takes a little bit longer time to interrupt. So this is good question, and it is important test which must be included in the test plan for circuit breaker.
Right. Thank you very much from my side.
Okay. Thank you.
Right. Thank you very much. Then I see we have one question on the DIU connection. We'll take that up later. For now, we'll move on to Work Package 4 and HDD Secret Protection System.
Hello, everybody. My name is Dirk van Echtem, and I would like to give you an overview of the results that we received within the HVDC Grid Protection System studies. Can you go to the next slide? Okay, so you can check with the video that was indeed me. So what did we do within this work package? So HVDC Grid Protection is actually a new problem in the sense that compared to a traditional AC system, the fault current rises much faster, the steady state value is much higher, and at the same time we are very sensitive and converters which cannot deal with high overcurrents for very long. It's really microseconds. So we need to protect the system differently. We need to be much faster, and we have new equipment that we needed, as just presented by Dragan. So what is a question that we tried to, or the questions that we tried to resolve within the work package 4 of promotion? The first question was, is it technically feasible? Can we protect the DC grid in a sensible manner? How to detect the faults, how to ensure selectivity, which kind of strategy do we want to use? Are we going to use the same way as we do in an AC system, or are we going to do it slightly different? What is the effect on the equipment requirements? And how can we compare and evaluate different types of protection approaches? Because if you have multiple approaches, then you need to know which one is the best. And in the end, we also needed to evaluate which protection system is good enough. So we had to go to a risk-based approach. The second question that we had is the equipment ready? Not about the protection, the breaker equipment, but on the secondary equipment, the IED. So we developed the necessary prototypes, and then we actually wanted to check whether this prototype also fulfilled the functional specs that we designed them for. So also the test had to be developed. We wanted to test beyond academic research and provide the evidence that DC grid protection is ready for the market and interoperable. And we also wanted to see whether this fancy new system, with much more expensive components, was still sensible from a cost perspective. So we looked at the effect of DC grid protection on the cost-benefit analysis. On the right-hand side, you can see the partners that contributed to this work package. So it was a group of many that contributed. You can see the different system operators, research institutes, vendors, and also consultancies that were involved. And next slide, please. So I'm not going to present this in detail, so I hope you all have seen the detailed presentations. They're online, so you can still do that if you missed some. But here you see an overview of our program, of the details. I will only focus on the key summaries. So maybe the next slide. Okay, so what are the key takeaways? So we believe that this project, and in particular the work in this work package, has de-risked DC grid protection through the development of a consistent set of requirements, analysis models and tools, and the prototype equipment. The work package has proposed the vocabulary and the functional requirements, because they were both non-existing before. It's something completely new. And this for fault clearing strategies for DC grids, as their scope goes beyond the traditional scope of power system protection. DC protection sequences, including fault detection, protective actions, and control actions, have been proposed for each of the fault clearing strategies, clearly showing that protection and control are fundamentally interlinked, and that technical key performance indicators to assess the performance of a given strategy have been proposed. The assessment of protection philosophies showed that several philosophies could serve as a viable technical solution, and an academic and industrial grade prototype IED had been developed, and they have been used to demonstrate principles of fast-acting protective relaying algorithms. You can see the two at the top one, the one developed within the project by KTH and been tested to the functional specs, etc. Also being used in Work Package 9, which will be presented next week. Below the version developed by Mitsubishi Electric, which is an industrial IED, which has been focusing on the, it could be placed in the substation immediately, while the KTH one has been developed for, let's say, flexibility, and it's an open source IED, as been shown in the last point. Next slide, please. So, as mentioned, we had these new devices, so we had to develop also the test procedures to evaluate the performance of these HVDC IEDs, and a risk-based cost methodology, cost-benefit analysis methodology has been developed, which allows to evaluate the cost effectiveness of different protection strategies, considering both the AC and the DC side reliability based operational expenses. We have found that the DC grid protection strategies could impact the frequency stability and the transient stability of the AC system, which are for those systems connected to the DC grid, which means that you actually need to do a quite an extensive analysis, also including AC stability, if you really want to develop such a system. We found that there is no single protection strategy that outperforms all the others. We have multiple working solutions, and they are competitive with all different advantages and disadvantages. But we have the different tools to evaluate them and to choose the right system for your particular application. While DC grid protection is comparatively more expensive than AC protection, we believe it is not blocking the development and the deployment of DC grids. And I think this was my last slide. So with that, I hope that there are some questions that you can ask in the chat box, but which I cannot see.
There are no questions yet. Just a second, please. Unfortunately, this worked. Give me a second, please. So while my PowerPoint is blocked, I'll read out the first question. So it's concerning one of the last aspects you just mentioned, that there are different protection strategies available, and that most of the methods work. So with all those disadvantages and disadvantages, advantages and disadvantages, is there, how can we choose one? Do we need to choose one? What are the different aspects that we need to take into the decision? And is there kind of a no regret decision one can take right now?
Okay. I don't know if you can still hear me. It looks like my computer has blocked. Okay, good. Then it's only part. Can you give the word to my colleagues within the project? I don't know if you can enable them, because we have several of the authors here present.
Who do you want us to?
Maybe you can, maybe Ilka can start, and Ilka, Mian, if Kamran is here, that would be nice as well, and Busat.
Working on it.
Ilka, you should be able to unmute yourself now.
Hello, this is Ilka.
Yes, we can hear you. Welcome. The connection
Hello,
seems
can you hear me?
Yes. There seems to be quite a delay in the connection.
Then maybe we skip myself.
All right, so the next would be Mian.
Seems that we're experiencing some technical issues.
Mian, you should be panelist now and can unmute yourself.
Hello.
Yes, hello.
Hello. Can you hear me?
Yes.
Okay. I think it's a great question, yet we did study quite a number of different strategies, and then they all have different advantages and disadvantages in terms of how fast can clear the faults, how faster we can restore the system, and also the extensibility of the protection strategy itself, and then cost, and etc., etc. So I don't think per se it's a problem, but it does complicate the solution a little bit more. In a way, it is an opportunity in the sense that we can use different technologies and encourage competition between different manufacturers, so we have more or better solutions also in the future. I think the important things we can take into account when we choose a certain strategy is that first of all, how do we want to protect the system, and what are the constraints from the AC system, from the DC system to solve? And do we want to extend the system? For instance, it's a small system when we plan it. If it's only a 3-terminal system, we might want a different strategy. But if in the future we want to connect it to a much larger grid, for instance, if it's an overlay European grid, then we might plan it also differently at the beginning, so we can provide a better solution from the start. So there are a number of questions need to be considered, both in technical and also in cost. I think maybe Jen and Bosad will give a little more opinion or insights on the cost benefit side.
Okay, maybe Bosad can comment on that as well.
Bosad, you should be able to unmute yourself now. You're unmuted, Bosad, but we can't hear you.
Maybe in the meantime, I'll read out another question quite related to the one we have right now, which is, taking into account that different protection schemes can do the job, is it recommended to standardize or harmonize protection requirements for an offshore HVDC grid in the North Sea? Is the flexibility for a grid build in stages to move from one, is there flexibility for the grid build in stages to move from one protection scheme to another? Maybe Dirk, you can directly answer if your connection works fine.
Yeah. So yeah, I hope you can still hear me. My connection is really not working as it should. So what we try to investigate during the project is indeed how flexible are we or how committed are we when choosing a particular way of protecting the system. If we choose one, are we fixed for the entire duration of or the lifetime of the system, which might have serious consequences? And there the answer is a bit mixed. So what we notice is that there is a possibility to interact multiple systems together, that we can join them, and it makes it a little bit more complicated. But at the same time, there are some choices that are, let's say, permanent. So if you choose to go for a solidly grounded system, bipolar, or you choose for a monopole solution, then it's not always that easy to connect those. So there are some limitations, and let's say the step in making
Unfortunately, connection broke off here. The joy of online seminars.
Ubisoft Technology, yes.
Jan, could you take over from here and complement what Dirk just stated?
Can you hear me?
Yes.
Yeah, okay. Yeah, I think what Dirk meant is, yes, there are certain choices are permanent. For instance, if we choose the voltage level, the grounding, the configuration of the system, first it would and of course also the transmission lines. You see, in Europe we probably will have more cables, but in elsewhere probably will have overhead lines. And all these, hello, can you still hear me?
Yes, we can still hear you fine.
Okay, sorry. All these different choices will have an impact on how we choose our system, how we choose and design our protection systems. So once these kind of things are certain, then in terms of protection strategies, for instance, we want to use a fault blocking converter or a fault feeding converter, for instance, as a half-bridge MMC, as a standard MMC we're using now. Then it comes a different cost and it's a different choices. We can at the beginning, for instance, if it's a small system, some examples are the Cobra cable system or the CMS system in the UK. They are designed as a non-selective strategy to start with, but then in the future, when we connect it to more terminals, to the third terminal, to the fifth terminal, then we can put breakers at different locations to either split the grid to different parts, so we can protect them. We can have a smaller impact when we have DC fault. And then when we evolve to a really large system, and we can probably put circuit breakers everywhere in the system and protect the DC system in a similar way as we protect the AC system. And during this, of course, the lifespan of the project or the lifespan of the DC grid development, we will also encounter cost reduction on different components if we standardize, for instance, DC circuit breakers or how the functionalities of converters. Then we will also reduce the cost of those components, will also enable us to choose a more or better technologies in the future. I'm not sure if Bussard want to comment on this as well. I saw he was connected a little bit earlier. Can you still hear me?
We can still hear you, Jan.
Yeah, okay.
Bussard, maybe you can try as well. You should be connected and unmuted.
He is connected and unmuted, but seems to have technical issues. So we may want to give the question to someone else.
Another option. So I think that summarized it really nicely what Jan said. With an eye on the time, we might move on as well. If Bussard cannot connect right now.
Yeah, he has
Right,
issues with his microphone.
Okay.
Yep.
All right, then I propose we move on, and if we have time in the end, we can come back to this topic and see if we can still answer the outstanding questions there, when maybe Dirk is reconnected as well. All right.
Christina, Bussard just mentioned that we may ask Serge if he could answer the question.
All right.
Serge is willing. Serge, you are unmuted, or you can unmute yourself now if you want to.
So, do you hear me?
Yes.
Yes. So, good morning, everyone. So, Serge Poulain. Yes, Bussard has some trouble with his speaker. So, I will try to complement some point about the first question. How far we can select the best protection system is not an easy question. I think that that has been said that main important is that the protection system will deal with all the requirements from AC and DC systems first, and depending on the requirement from mainly AC systems, stability, from transient stability and frequency stability, the selection of protection system could be different because they are different performance and also different costs. So choosing the best trade-off between performance and cost needs full assessment studies using all many of the tools we have developed in Work Package 4. And we can say that if the requirement from ASC systems will be maybe some of the main driver to select the protection strategies, and then if the choosing a protection strategy with respect all the requirements, we can expect to try to select the strategy with the best cost regarding the fulfillment of requirements. So in other terms, it's always a trade-off between the cost and the performance of strategies, and we need first to respect all the requirements and then to try to select the strategy with the best cost. Also, the extensibility aspect could be also be property to look at, and we can say that all strategy could be quite extensible, and that there is no real restriction. And if we implement, as said Miam, some partially selective strategies or grid splitting, we can also think to associate to make operating several protection strategies together by using dedicated firewall, such as fast DCCBs, as the interface between the different protection zones will be protected by a different protection system. So it could be also an option to put in advance regarding extensibility of protection system. So I think yes, it's okay for me. So
all right.
I hope that the sound was nice.
Yes, we could hear you clearly. Thank you for the explanation.
Okay.
So we have one more question, but with regard to time, we'll go over to the next section now. We either get back to it in the end, or we'll get back to you via email. It's on the interface between control and protection. So thank you very much to everyone for this Q&A session, and we'll move on now to Work Package 3 on wind turbine grid forming control.
Yes, hello, and thank you, Christina, for the introduction. We are moving now to the Work Package 3, which is moving towards the wind power plant and its control and interaction with the HVDC transmission system. My name is I'm Nikos Koutouloulis. I'm coming from DTU, Technical University of Denmark, and I've been working for many years in the wind power integration. And in the project, I was fulfilling mainly the role of Work Package 3 leader, and that's why I'm also presenting today. So Work Package 3 was mainly focused, or when it started looking at ways of reducing the cost of offshore wind transmission, and to do that was looking on a very specific or a concept of using a diode rectifier unit as the offshore converter, and this while using a diode rectifier the diode rectifier as a component is not necessarily something new, but in combination with offshore wind farm, that would require that the wind turbines need to develop a grid forming operation mode, so to be able to form the offshore AC grid. And that was also a big part of the focus in the project. And a little bit later, as things are developing fairly fast, we start looking also on, by using this grid forming operation mode, if we can provide more advanced reliability services from wind power plants. And we looked on black start operations, so ability of offshore wind power plants to support the black start on the onshore grid. And like the other work packages, we had a good number of, or was a large work package with a good mix of academia, OEMs, TSOs, and consultancies. So I hope, like everybody else, that you have watched the detailed videos on the many results we have obtained in the project. What I will do now, I will try to bring up the main points that we think are coming out from the work we have done. So as I said, coming to the diode rectifier concept, this was fairly new way of operating an offshore wind farm. So we did a lot of work on defining all the functional requirements, scenarios, and test cases to validate DU capable grid forming controllers for wind power plants. And we did that validation in simulation in all modes of operations, for normal operation, also looking at transients like faults, but also covering other aspects like ancillary services provisions. And we did that with a large number of cases and test cases and situations. And one of the points that coming out is that standard grid forming controller seems to be able to work with DRE connection with not necessitating very large modifications. And based on all this experience that we gained and knowledge that we developed with the DRE operation during the project lifetime, we made a document with some recommendations of requirements that should be applied in case of diode rectifier unit operation. The second part of the work package, as I said, looked at black start, and here we did validation of controllers, both from generic academia developed one, but also from vendor specific black box model from the industry. And similarly, maybe with a diode rectifier unit, when we're talking about black start from wind power plants, offshore wind power plants, we also had to look what would be the functional requirements and what are also the possibilities and the limits of wind turbines to provide that. So I think one of the main points that comes out that if the requirements are adequate, then black start operations from wind turbine generators can be provided with partial or rather small modifications. And then those modifications, of course, impact a lot, means a totally different control solutions, which also means a new certification process. And of course, depending, that will also mean that you might require local wind turbine storage to be able to start up at least one wind turbine. And then when we look at the different ways of energizing the offshore network, we saw that by if we do a sequential start or a hard switching, that might lead to over voltage and current, of course, due to the inrush currents of ferromagnetic oscillations, and it can also take a relatively long time to do that. Of course, there are methods for doing that, or trying to reduce the impact of the large transients by using either point of wave switching or pre-insertion resistors, PIR. Then we as an alternative, next slide please. Then as an alternative, we also looked at soft start, so trying to energize the whole system in one go with ramping up the voltage, and that showed that it leads to a faster energization and minimizes the inrush current and oscillations. And Of course, when you have such a large number of wind turbines operating in a grid forming way in a system that is being energized and start up, fault recovery is an important aspect of that needs to be taken care of. And of course, finally, I think we saw that the grid forming control, the solutions there, and this is a fairly open area on what grid forming control philosophies are the best ones, but they have to be robust to large changes in resonant peaks, and also they have to be able to interact with the other converters and generators in the same area. So trying to summarize for the wind turbine grid forming part with the DRU operation, we think that based on the results that we had in the project, that they can it's a possibility they can operate with a diode rectifier unit, and we have done a very comprehensive procedure starting from defining the requirements, defining test case and scenarios, defining compliance procedure, and then applying all this compliance procedure and simulations. We have created a very comprehensive procedure provided for validating the controllers for wind turbine operating with diode rectifier unit. And similarly for the black start part, grid forming wind power plants can contribute to speed up the system restoration, but more work there is need to align technology development, the technical requirements coming from the DSOs, and also of course the business model on how to deliver this part. And I think this is my last slide. Thank you.
All right, thank you very much. We don't have questions yet here in the chat, so I'll check on the pre-sent in ones. They should be on screen now.
Yes. I think probably the first question, it's maybe more for the industrial partners in the project. I don't know if anyone is present in the chat.
I know several people from Siemens Online, if you're referring to Siemens, for example.
Maybe I was also thinking about maybe Ørsted or MHO Envao, or if not, maybe then I can try to address that. I think that in the project now we have made very important steps into de-risking the concept of diode rectifier unit, and I think we have shown with very deep and large pool of simulation and test cases that wind turbines can't operate in a grid forming mode and can't operate connected to the diode rectifier unit. And with in VP16 we also moved this to validate the control hardware in the loop. Controllers in a control hardware in the loop setup in the laboratory phase. So I would imagine that a next step would be to move towards a real life or a real size demonstration of the project.
I think Markus Teller from Siemens is online and should be able to comment shortly if we want to have one, although not directly involved in work package 3.
Well, I would be if he would like to comment. I think he'd be okay. But as you said, I don't think he has been directly involved in VP3, so I'm very fine with it.
All right.
If you have some time, I can add a little bit more.
Oh, Ramon, please.
To what Nikos said, I agree totally with what he said. I think it's a matter of de-risking the whole concept at a reasonable power level. And at least we have provided in work package 3 and in work package 16 a process for the validation of these grid forming controllers. On one side, grid forming is going to be a real thing in the medium term. There are many vendors that are going to go ahead with that, and changing the grid forming controllers to operate with a dial rectifier is a small step. So sorry about that. The point here is again getting a process into reasonable power demonstrator. I think that would be again the point once manufacturers are aligned with the grid forming, etc. And I think that this is probably coming along in the medium term as well in some projects around the world. So well, if the DRU can deliver the savings that are claimed, I think one way or the other we'll have some DRUs operating in the medium term.
Yes, thank you very much, Ramon. If anyone else from the attendants, I cannot see the list of people besides the panelist who is present, but I don't know if anyone else wants to comment on that or.
So we have neither Lorenzo from Ørsted online nor Tracita right now. I guess those were those which you might have had in mind.
Yes, but then okay, maybe we can move to the second question, which is somehow related, I think, or in the similar direction as the first one, related to Black Start. And maybe I could actually give the word first to Ramon or Anubhav or some other of the project, of the people that were part of the project, and maybe they can say something about that as well.
Ramon, do you want to start?
Yeah, I think Black Start operation is going to be the first step. Probably, I cannot speak for Lorenzo, but what he said on his nice presentation that is online is that at least islanding operation is something that developers see as a very positive functionality for offshore wind farms. So I could see that coming in the pipeline in the new projects to be developed. There are also manufacturers who are trying grid forming, and moving that grid forming capability to islanding is going to be the first step. And then for Black Start operation, I think the technical capability is very close there. But the main issue is to find out business model for both manufacturers and developers to see how this additional development effort is going to be financed and how they can get their business aligned with the new technical capabilities. So the next step forward is going to be developing, obviously, the islanding capability, and then from that move into Black Start. But it's something that is logically going to happen, because if we're going to have several hundred gigawatts of renewables during a blackout, it's not logical not to use that for their service restoration.
Thank you, Ramon. I agree with Ramon, and I don't think it is very much I can add to that. But the same, I think, here would be the next steps would be to move to a demonstration to a reasonable higher power level, maybe initially with a single wind turbine, and moving up to a wind power plant showing this capability. I think if we move to the third question, I think energization, yeah, energy, it's that's true. One of the characteristics of the diode is that allows for power to flow in one direction only. So it require when we have an energization process, we will have to find alternative ways of doing that, alternative to the standard way of providing it through the transmission system, the onshore, from the onshore towards the offshore. And this is an open subject. I think there have been several proposed ways of how to do that. One of it was by using a separate AC cable and a so-called umbilical cable that will connect from the onshore AC system to the offshore AC network of the wind farm, and that will provide the initial power and to energize the offshore AC system. Then one can think of different other ways of doing that. I think it was proposed by having maybe a much smaller in terms of rating VSC converter offshore that will allow for this this directional of power flow, or maybe connected to a neighboring wind farm and so on. It's a subject that will require more investigation, and of course you will have, depending on the technical solution that is going to be used, might have some impact on the way, on the process or the procedure of starting up the offshore wind farm. I don't think it would be, but I don't think this would be very strong. The next point, I think it's fairly detailed, and I'm very curious if Oscar, my colleague Oscar, is online, because I think he's been working with the ancillary service provision.
Oscar, you can unmute yourself now.
Hi.
Hi, Oscar.
Hi. Yes, I guess the question is related to DRU connected wind turbines, and it's
yes.
a common question. That it's counterintuitive for people that are used to, for example, VSC connected wind farms. The responses that we presented in the video reflect characteristics that are specific or special for the case of diode rectifier connected wind farms. Such as the fact that active and reactive power flows through the diode rectifiers are not decoupled, and that physical coupling between the active power and the voltage magnitude in the offshore network arises from the fact that the active power flow through the diode rectifiers is determined by the voltage difference between their AC and DC terminals. So the fact that the voltage is used to control the active power flow, but in changing the active power flow, there's as a result also a change in reactive power flow and frequency. It's something that is unique or specific to diode rectifier connected wind farms.
Good. Thank you very much, Oscar, for the answer. And then if we move to the last two questions, I would maybe ask Anufra if he's online on the choice of grid forming control and how important it is in the black start process. And of course, Ramon can also answer that, but maybe Anufra, if he's online, can answer that.
With the eye on time, please keep it brief. We have to move to further sections.
Yes,
Sure.
hi, can you hear me?
Yes.
I'll be quick. We have actually published a study about this question. So basically choosing different grid forming controls does impact the performance of the wind power plant during these energization transients. And the reason is because some controls, some have power synchronization, for example, power synchronization controls or synchronous machine-based controls, and then you can have direct power controls. So due to their inherent characteristics like decoupling or 50 hertz resonant peaks, so they can show certain vulnerabilities to instability. Of course, it depends on the topology of the wind farm and many control parameters. However, there is a certain tendency that we saw in how different grid forming controls behaved, and I can send a link on the chat, but I don't know if that would be visible to everybody if somebody wants to follow up more in detail.
Please do send us the link and I'll make that available for everybody.
I just sent it on the chat, and I don't know if you see it, but I think you should be able to see it.
Okay, and then I think we will we will take the last question and maybe answer it later in written format to save the time for the rest of the presentations. So I will say thank you to all my colleagues that presented, and yeah, ready to move to the next one.
All right, thank you very much. It's actually, yes. So welcome everyone also to this presentation on Work Package 2 on converters and topologies. What was the main aim of Work Package 2? So the objectives were to perform a trade-off analysis of different topologies, so taking into account different grid structures that might evolve, starting from smaller ones to bigger ones, for different operational strategies and also for the grid planning phase. And then we have the interconnection of the voltage source converter and direct rectifier unit systems. So what was just discussed in Work Package 3, there were a lot of detailed studies on the controls of the offshore wind farms, how to enable the connection to the direct rectifier systems. And then there was also the aspect on the control concepts to ensure interoperability. So for example, having a parallel DC link with a wind farm and a parallel DIU link or an AC link connected on the AC side. So this is also what one of the questions is alluding to, which was also briefly answered before, if there needs to be a certain source for the startup of the system with the DIU. And then bringing this broad range of studies together, the final objective was then to define recommendations on onshore and offshore power systems for the existing grid codes. So just to give you a brief overview of the study aspect, so within Work Package 2, we discussed the normal operation and system design, so different operational strategies. We had a look at what is the impact of the DC side faults and contingencies on the connected systems. So for example, on connected offshore wind farms involved in HVDC systems. And also, as just presented, check how the direct rectifier unit can be integrated into multi-terminal radial or mesh structures on the HVDC side, or also connected on the AC side. And then also we had a look with the systems becoming bigger and bigger, how do these affect AC system dynamics, or how can we use the systems for auxiliary services, as also alluded to before with the direct rectifier support. And here we looked at HVDC systems based on VSCs and checking different frequency support options. So this was also based on a large number of partners coming from academia, the HVDC manufacturers, consultancies and research institutions. And so here I'll present you some selected key conclusions. So also closely linked to the videos we uploaded if you want to have a look at the detailed topics afterwards. So the first one is the feasibility of direct rectifier integration into the HVDC system. So there was a proof of concept for the different control concepts for the AC side connection, but also for the DC side connection and the overall system behavior. And then we had a look at the system planning and operation and the contingencies. So checking how bigger combined AC and DC grids can be simulated, especially for the grid planning phase. So still using RMS simulations, which allow bigger system analysis. And also a security constrained optimal power flow, so checking how to operate integrated AC-DC systems, and there the operation of DC systems will be quite different. For example, rather using curative measures instead of preventive measures in the future. As just already mentioned, another part that is supposed to be part of the function of an HVDC system is the frequency support of the connected AC systems. And there's a variety of frequency support concepts considered. So via the offshore wind farms, via the HVDC systems, and there are also different implementations then. So purely control-based communication-less approaches, just working, for example, on DC voltage variations and of course the frequency variation. But when checking all those different options for more complex grid structures, it became clear that the communication-based strategies right now are better suited to fulfill the regulatory requirements. And then, of course, what's more and more important with the DC systems is EMT simulation. So that was also a big part of the investigations in work package 2. And here, a selected aspect we presented here is the interaction of the HVDC system and connected AC systems, and here especially the offshore wind farms under fault conditions, because for the existing DC systems, the point-to-point links, the wind farms will be shut off in case of a fault on the cable, for example, and it will also take several months until the cable is repaired, or weeks at least. And for this time, the wind farm will not be connected. But with the multi-tunnel systems, we really want to achieve fast power flow recovery. So the wind farm should be able to ride through whatever is the impact on the offshore connection point, for example, using different fault clearing strategies. So we investigated how is the impact of the different fault clearing strategies on the offshore wind farms. And then also there's a proposed control concept to ride through the most demanding scenarios for the offshore wind farm. And then the last part is the recommendations towards HVDC grid codes. So there is the NSOE HVDC grid code and then current national implementations on this, which specifies the AC side specifications for the integration of existing HVDC links, where the HVDC link is seen as one system, but there are no yet specifications for the requirements at the DC point of connection. So when we want to enable those larger multi-terminal systems, we also need to have specification on the DC side, and when we try to derive at those, that's still very challenging because, as you've seen before, there are a lot of options to control the system, to design the protection strategy, a lot of different components that could be used. And while in general there are a lot of possible configurations to write a grid code that would apply to all these technologies, is still very challenging. So there's also a deliverable on this where you can see how we discuss the different aspects that have to be taken into account and that might be the first steps towards the HVDC grid code. So thank you very much for your attention, and I'll check the questions now. So there was one that was posted before. I think it was alluded to before with the AC side connection. So it's directly related to the pre-recorded seminar on the diode rectifier with a parallel link on the AC on an AC side and then VSC link. So maybe Markus Zeller could comment on this. I'll read out the question in the meantime. So
hello, Christina, can you hear me?
Yes, we can hear you well.
Okay,
hello, Markus.
Great. Yeah, hi.
So the question we received is, with respect to the pre-recorded seminar on diode rectifier, the first part indicated that some form of AC backfeed was required to the wind farm connected to the diode bridge, active for turbine aux power and reactive power for voltage control. However, in the second part, a hybrid solution was shown with no AC infeed. Please clarify if the diode solution is feasible with no AC backfeed from shore or neighboring wind farms.
I'm not sure if I got the question right.
Try to put it on screen.
Well, can you put it on screen, please?
Yes. There you go, the first one.
Well, I'm not completely sure about what the first and the second part should be. So in our part of the work package 2, we have considered the parallel connection of the diode rectifier unit in parallel with a VSC link, an existing one, and also an AC cable. And the idea was to show the interaction, so the feasibility of a combined operation of all of these systems, because the assumption was that, okay, there will be existing VSC links as of now and also existing AC connection of wind farms. and it was shown that this could be operated in parallel with a new connection via DRU solution, and it was shown that the controls could be set up like it was shown in the slides, so that actually no major changes to existing controls would be required. So
I can also comment on that if you want.
Yeah.
Yeah, Oscar, go ahead.
Yeah, please go ahead. Yeah.
Yes, maybe related to no AC infeed. We published a study in which we analyzed and proposed controls that would allow the, so it was based on the combined topology that Christina was presenting, having one AC connection, one VSC HVDC connection, and one DRU HVDC connection. And we showed that the AC connection could form the offshore AC network, could provide the voltage to the offshore AC network, but in case of that AC connection tripping, becoming not operational, the VSC could seamlessly take over. Maybe that's related to the question. And I can, just as Nuhab did, I can also provide a link to the paper related to that.
All right. I think the next question is in a similar direction. So could you comment on the technical feasibility of direct rectifier connected wind power plants to be connected to meshed grid or internet connectors? What would be the technical hurdles? I think one part there was from Ramon, if you want to comment.
Well, I think in work package 2 there was quite a lot of work done on the technical feasibility for direct rectifier connected wind farms to both on the DC side. There was both on the AC side the parallel connection that that Siemens did. That was a very nice a very nice example on how the direct rectifier connection can be carried out without even modifying the wind turbine controllers. I think going forward, it is also an interest on connecting that on the DC side. And normal operation is, what we have seen is that normal operation is really relatively feasible. The main problem comes with fault handling. And I think the integration of direct rectifiers in both interconnectors and mesh grids can be done, but there's quite a lot of studies to be done with fault handling, particularly trying to avoid the use of DC circuit breakers, because if we add the DC circuit breakers to the DRUs, the simplicity of the DRU somehow gets lost, and the cost advantage also gets lost a little bit. So especially if in some of these solutions can be done with very inexpensive DC circuit breakers or without DC circuit breakers, I think that that would actually help the DR system connected into interconnectors or HVDC grids.
Right. Thank you very much. So I'll briefly get back to the next two questions. So what role will grid forming controls play in future HVDC grids? So I think we had a lot of examples where grid forming controls come in here. The interaction I just mentioned, or that was is in the video 4. So for the DC fault right through, we might also need a certain grid forming control from the offshore wind farms. We'll need it for the black start. We'll need it for the DRU. So I think that there has been a lot discussed with this. If there's more specific question on this, please get back to us. And then another question is, when will a plug and play HVDC grid code become available or be available? I think that's a very difficult question. This will still take some time. And the question is also if there will be a plug-and-play HVDC grid code similar to the existing AC systems, because with the converters being a fully controlled component that is right now specified, or the control mainly is basically done by the manufacturers and under the IP right, it will be more difficult. There will probably need to be more interaction studies, or you need more interaction studies when integrating an HVDC system. And the aim of the HVDC grid code should be to, or any functional specifications also, for example, in Senelec standards, should be to reduce the interaction studies needed. But if we get to the point where you can just plug and play an HVDC converter into an existing system or another component, that's very difficult to answer right now from the existing status quo. But this is also, I think, a nice transition to the next section on harmonization towards harmonization towards standardization, because there we discuss which aspects we have considered for standardization of HVDC grids. So I'll hand over to Paul Sorensen here.
Thank you very much, Christina. You hear me?
Yes, we can hear you fine.
That's good. I also try to put on my camera now. If yes, so welcome to this the last presentation, I think, from Work Packages today, and it's also kind of a wrap up as well. You can see that. So this is on the harmonization towards standardization that we have been working with. My name is Paul Sørensen, and I am also like Nikos Koutoulouris with and some of the other who have responded to in the Technical University of Denmark. I have professorship in wind power integration and control. I worked more than 30 years with research in this area, and then I'm also involved and have been for a long time involved in standardization in the wind energy community, where I'm convening the standard on where we are doing generic simulation models for wind power plants, and also for a long time we have been working with test procedures and measurement procedures on wind turbines. Then my role in the project is that I'm leading work package 11. So you can go to the next. So what is the purpose of this work package? Is first of all to harmonize industry's best practice and into standards, and also support this harmonization of best practice and standards and requirements. Also grid codes, we have also been working with that. And the idea is the drive is to make sure that we are taking the findings in promotion projects. We are taking them one step further than publishing them, but we also directly communicate this with standardization and harmonization groups. We also try and contribute to harmonize, because there are several harmonization groups and standardization groups, but we have also worked on understanding and following the activities in different of those groups. And finally, it's important, not only actually in this work package, but in all the investigations we have done in promotion, that we are considering as many manufacturers' concepts as possible. And this is a possibility we have because we have several manufacturers, OEM manufacturers in the project. So what type of outputs are we providing? This is not completely covering, but I think the main things are like functional specifications and requirements, recommendations to that from our side. Also, you have already been seeing, and you will see also next week, that there has been going a lot of test activities going on also in the project, and this has also resulted in inputs to what is good practice in doing tests. And And then we have also in the work package, we have had an activity where we looked at compliance validation and what should be the requirements and methodologies to that in the future. So next. Yeah, so I have copied Christina's nice drawings here to illustrate also harmonization part, and as yeah, this is very much about how we go into the harmonization of multi-terminal HVDC grid. You can say at the system level, this is the work package 2 in promotion, which Christina was just telling about here. That is the main contribution, and here I'm showing in red not an exhaustive list, but what I could see as the most important harmonization or standardization groups that we have contributed to. So there is a new standard on cell elect which we have been following and contributing to on HVDC system aspects, also to contribute to the vocabulary. There is a Secret group on DC systems, and also there is the dedicated IEC technical committee, which is making standards and HVDC systems. So to the next, on the DC protection systems, there is a working group or there is a technical committee on protection systems, and this one has started a new working group on DC protection, which or there is work on starting that, and we have communicated with that technical committee. And then as you see here with IEDs, communication plays a very important role. So there is also interaction, and we are also communicating our findings to the IEC technical committee, which is dealing with information exchange. Then regarding the circuit breakers, there is Secret working groups, and also there is a technical committee in IEC on high voltage switchgear, where we have also are also communicating the work, the findings we have on in the regarding circuit breakers. And that brings us to the next, actually, also as a supplement to this, also the GIS, which Uwe has explained very well in the morning about. And here there's also, Uwe also mentioned, there's also a Secret working group, but first of all, also now there is a new standard group in a standardization group within also technical committee 17 on GIS switchgear. So next, I think it comes, yeah, as you mentioned also, Christina, on the control activities, and there is a Secret working group there, which is working on interoperability in between converters. And then the next one, another aspect which is actually very much related to interoperability is what is here called the impedance models. So this is the multi-frequency modeling, which plays a very important role for interoperability between the converters that we have in the power system. So and this work is there's been specific work in work package 16 related to VSC converters, and there's actually also work related to wind turbine converters in that direction. So maybe we can just go to the wind turbines to the next slide, or the wind power. In the wind community, there is quite a clear distinguishing, I think, between the different areas of standardization. We have the test, as you can see to the right. We have modeling, and then also there is work on compliance evaluation. I would say the first they are the first one on test is very mature. The one on modeling is also there are standards already, and finally on compliance, it's on the way. How do we evaluate that wind power plants are complying with the requirements, specifically in grid codes? So first, we heard already, Nikos and Ramon were telling about the activities on black start and diode rectifiers, especially from work package 3, also of course a little from work package 2 here. And this from these activities, we have recommendations regarding modeling and compliance evaluations, because there has been done some compliance simulation in work package 3 also. So you can take the next. Regarding multi-frequency stability, there has been work in work package 16 in demonstrating how we can measure impedance at the different frequencies. And also work package 16 has, that was also mentioned, I think, by Ramon, the demonstration of black start capability. So the next one, the last one, Christina. That's actually, we have also done a little research in work package 11, but although our main role has been to communicate findings from other work packages, we have made and communicated a paper on test bench specifications for wind turbine nacelles, and also we have been working on theory in multi-frequency stability, where we have added focus on the different couplings between the different frequencies, and also there are couplings between negative and positive sequence, and this is something we have added to the findings that are already demonstrated. So I think this is it. Are there any questions?
I don't see questions in the chat right now. Maybe one short message to all of you. We're a bit over time. We'll probably we'll try to answer any questions right now, and then we'll have the conclusion. So if you can bear with us with a few more minutes, that's nice, but you can also just check the end. So let me check. We had a few questions beforehand. Two questions mainly about the input towards the standardization groups. They should be on screen now.
Yes. So what? How we are communicating our findings to standardization groups? Yeah. First of all, I mean, we started, as I mentioned, also identifying who those relevant standardization groups are. And then several of the participants in promotion are actually very active in this already. So, but that's the easier part. But we try to structure it a little more also. And what we have done is that we have made fact sheets which are more targeted to the harmonization groups. We have made several reports also, but we have tried to condense the communication in very specific fact sheets and targeted them to specific working groups. And then are we considering to propose new working groups? There are already new working groups that have started. I think maybe you mentioned it, Uwe, already, but actually the GIS working group was initiated and led by Uwe, but also we are having in the pipeline the idea to propose on the wind side new working groups. It's clear that there is a need for more standardization in multi-frequency area. This is right now, it sits at Secret level, which is more at best practice level, but we think that there is a need also for IEC standardization in that end. And also regarding, that's actually the same, there's work going on regarding EMT modeling, good practice. We can probably not make generic models, but we can specify requirements to models, and also we should standardize how we should validate those models. Validation is very important, and validation of models, and this is also a part of compliance evaluation is about doing simulations, but then it's when we do simulations, when the grid operators are doing it, then it's very important that they can rely on the models, so that that this validation is a very important thing, and the subject to harmonization standards. So that's it.
Thank you very much. Then we'll come to the conclusions and outlook. So thank you very much for being with us here. Thank you to all presenters, to all questions, to the panelists and the discussions right now. So what's the main message that we have from the project is in general that the technology and the concepts are there for multi-terminal HVDC grids. So on the one hand, this relates to the HVDC grid control, where different controlled concepts have been proposed, tested, compliance evaluation procedures proposed for the wind farm, for the different systems. There's still the topic, as was just mentioned, is, for example, the EMT models and the proprietary controls of the manufacturers. So there are still a lot of interaction studies needed to ensure that those work together while the general concept is working. Similarly, for the HVDC grid protection, as was discussed before, there are several concepts proposed and feasible for the offshore systems. Also, the technology with regard to DC circuit breakers, there's really been a fast development in the last years. And also with regard to the HVDC gas insulated systems, there's been quite a big step within promotion. All of these pictures here really also allude to the demonstration work packages. And I'd like to invite you to also join the next sessions of the final conference. So you can always get back to our session and the recordings and the presentations on the website, but then next week will be another session on HVDC technology qualification, so all the demonstrations that took place within promotion on the different technology aspects based on the work we just presented. The presentations will go live on Monday, and there will also be another live Q&A session where you can get in contact with the respective presenters next Friday. And also two other aspects, less technical, but nevertheless really important, which are the legal, regulatory, and economic aspects. So we really have to bring the whole system together from a lot of different countries to facilitate this offshore grid. This on the one side, the technical facilitation, but also the regulatory and legal facilitation. And this then also based on the technology and the regulatory framework and the different frameworks. Then the last session is on meshed offshore HVDC grid planning. So what will be the steps in the system? What are needed steps in standardization or collaboration between the different countries and operators? And then we'll have the final conference day where it all comes together with a live panel discussion, which you can also, we would like to invite you to join on the 21st of September. So with this, thank you very much for your attention. We couldn't answer all questions right now, so we saved them, and we will get back to the questions after the session, probably next week. So all questions will be answered, we'll make sure. And we hope we could raise your attention. If you want to get back to us, watch the videos, contact us, or join the other session, we're happy to get in contact with you. Thank you very much, everyone.